Welcome to Dr. Sherry's Astronomy channel. The theme this time is, the collision of the Milky Way galaxy and the Large Magellanic Cloud, unraveling the phenomenon of gas stripping. The Large Magellanic Cloud, which is visible to the naked eye in the southern hemisphere, is the largest satellite galaxy of our Milky Way and has captivated people with its beautiful glow for centuries. Along with the small Magellanic Cloud, it is known as the Magellanic Clouds and continues to interact in complex ways with the Milky Way galaxy. By studying this interaction, we can gain important insights into the process of galaxy evolution and cosmic phenomena. In the universe, which is thought to have begun with the Big Bang, galaxies have grown through repeated collisions and mergers. These collisions and mergers have been ongoing since the early universe, and are key factors in the formation of the large-scale galaxies we see today. The relationship between the Large Magellanic Cloud and the Milky Way galaxy is of great interest as it provides an ideal target for observing the ongoing process of collision and merger, which is essential for galaxy evolution. The Large Magellanic Cloud, together with the Small Magellanic Cloud, is strongly attracted to the Milky Way, with both galaxies affecting each other. This gravitational interaction has caused significant changes in the gas environment surrounding the Large Magellanic Cloud. The gas structure surrounding the Large Magellanic Cloud is highly complex, with several distinct features. For example, there are gas bridges known as the Magellanic Bridge, gas flows that stretch out like tails called the Magellanic Stream, and another gas structure called the leading arm. These features are part of the Magellanic system created by the Large and Small Magellanic Clouds. Particularly noteworthy is the Magellanic Stream, a gas flow that extends about 200 degrees across the sky, containing a mixture of different types of gas. This gas flow is thought to have been stripped away from the Large and Small Magellanic Clouds. The main forces responsible for the gas stripping are thought to be twofold. One is the tidal force caused by the gravitational pull between galaxies, and the other is the ram pressure that occurs when gas is pushed away as galaxies move at high speeds. These interactions are believed to have led to the formation of the complex gas structures surrounding the Magellanic Clouds. Recent observations and computer simulations have revealed the existence of a gas layer surrounding the Large Magellanic Cloud, known as the corona. This corona consists of ionized, high-temperature gas that is spread thinly. It is believed that the large mass of the Large Magellanic Cloud has played a role in its formation. The estimated mass is more than 100 billion times that of the Sun, and its strong gravity helps attract and maintain the gas. The gas stripped from the Large Magellanic Cloud may be supplied by this corona, providing a crucial clue to understanding this previously mysterious phenomenon. For example, the presence of large amounts of ionized gas in the Magellanic Stream could not be fully explained by tidal forces or ram pressure alone. Thus, the corona is suggested to play an important role as a source of this gas. A research team, led by Dr. Mishra from the Space Telescope Science Institute in the US, has recently studied the properties of the corona surrounding the Large Magellanic Cloud. They analyzed how light from a background quasar changes as it passes through the Large Magellanic Cloud. Using this method, they were able to directly measure the density, temperature, and composition of the gas surrounding the Large Magellanic Cloud, allowing them to study the high temperature, low density gas of the corona. By observing the absorption of ultraviolet light from background objects, they could analyze the gas's density, temperature, and composition. In modern astronomy, there are many telescopes available, but only the Hubble Space Telescope is capable of observing ultraviolet light. While the James Webb Space Telescope has demonstrated remarkable performance, it focuses primarily on infrared observations, and the Hubble Space Telescope's ability to observe ultraviolet light remains essential. Ultraviolet light with wavelengths shorter than 400 nanometers is blocked by Earth's atmosphere, making it difficult to observe from the ground, so satellite-based observations are required. Currently, The only satellites capable of observing ultraviolet light are the Hubble Space Telescope and the Swift satellite. Due to its larger aperture of 2 meters compared to Swift's 30 centimeters, the Hubble Space Telescope offers superior performance. In particular, the cosmic origin spectrograph onboard the Hubble Space Telescope has a high-precision ability to measure ultraviolet wavelength, allowing it to identify various metal ions within the corona and measure their physical states. For example, the graph shown illustrates the observed data. The graph shows data for 9 different types of metal gases. Thin gases, such as those found in the corona, are faint, but by focusing on metal gases that absorb specific wavelengths of light, researchers can investigate their movement and ionization state. Particularly, ions with lower energies, like oxygen, aluminum, iron, sulfur, and nitrogen, as well as intermediate energy ions like silicon, are used to study the motion of the cold gas at around 10,000 degrees. Data from high-energy ions are also included for a more detailed analysis. The red line represents low-energy ions, while the green line shows high-energy ions. The absorption patterns reflect the speed of the gas. For instance, areas where gas is moving faster show changes in the absorption lines. By analyzing these patterns, researchers can deduce the speed at which the gas is moving. The study found that each type of metal gas has different densities and speeds. The research team used 28 quasars to measure absorption lines and conducted an investigation of regions up to 110,000 light-years from the Large Magellanic Cloud. This measurement revealed that the size of the gas halo surrounding the Large Magellanic Cloud is about 50,000 light-years, which is only about 10% the size of halos surrounding other galaxies of similar mass. This suggests that when the Large Magellanic Cloud approached the Milky Way, its surrounding gas was stripped away by the Milky Way's massive gas halo. When gas is completely stripped away, new star formation is unlikely. However, the Large Magellanic Cloud still retains some of its gas, allowing for continued star formation. Based on these observations, the research team has depicted the collision between the Milky Way and the Large Magellanic Cloud as follows. In the diagram, the Large Magellanic Cloud begins to enter the Milky Way's enormous gas halo. The bright purple arc represents the shock wave at the tip of the Large Magellanic Cloud's halo, which is being compressed by the Milky Way's halo. As the Large Magellanic Cloud moves closer to the Milky Way, part of its halo is stripped away, and the gas tail is blown backward. This gas will eventually fall into the Milky Way. As the interaction progresses, the tail of the Large Magellanic Cloud becomes more defined. However, the halo of the Large Magellanic Cloud remains compact, and even after it passes closest to the Milky Way, some of the halo will remain intact. In this process, the Milky Way's gas halo compresses and strips away much of the gas from the Large Magellanic Cloud through ram pressure stripping. Additionally, the dense gas environment of the Milky Way applies strong forces, forming a comet-like gas tail behind the Large Magellanic Cloud. These observations provide crucial insights into the relationship between a galaxy's halo and its surrounding environment. In particular, they shed light on how the Large Magellanic Cloud continues star formation while being influenced by the Milky Way as it evolves. This study offers valuable knowledge for understanding how galaxies closely interacted in the early universe. Thank you for watching, and I'll see you in the next video. If you enjoyed this video, please don't forget to give it a thumbs up. Hit the subscribe button and the notification bell icon, so you'll be notified when new videos are released.